Student friends, I'm back again with another video regarding the spherical symmetric potential. In this particular video, we'll show how the hydrogen atom problem can be solved for the radial part of it. Already in the last two videos, we have shown how the spherical symmetric potential is defined, how the reduced mass concept can be used for finding the time independent Schrödinger equation for both radial part as well as for angular part. And also in the last part we mentioned the part dependent on relative coordinate can be separated out into radial part as well as angular part. So let's start. The potential for a hydrogen atom problem being as given by equation 1, it's Z squared by R, and it's a minus sign confirms that it's an attractive potential, and Z is equal to 1 for hydrogen atom. So 1 by R is the Nash-Horner Coulombic potential. Putting this in the time independent Schrödinger equation, and we're recalling back in the video where we have shown how the Schrödinger equation is represented in the spherical symmetric potential. We see that this equation 1 leads to equation 2 as far as time independent Schrödinger equation is concerned. So to solve the equation 2, we put a dimensionless variable rho equal to sigma r, and putting c back in 2, we get an equation 4 where our new coordinates are rho instead of r, where rho is as given by equation 3, sigma r. And also know that sigma is defined like this. Sigma square is a real kind of thing, is a real quantity. So it's, since E is a negative quantity, it's a bound system, so this minus 8 mu E by S cross square is simply a positive quantity because E is negative. And also choose another parameter lambda defined by equation 6, twice mu Z square S cross square sigma, or using 5 bracket here, we can find that lambda equal to this. And using 5 and 6 and 4, we get equation 7, 1 by rho square d by d rho, rho square dr by rho d rho plus lambda by rho plus 1 by 4 minus L into 1 L plus 1 divided by rho square into r rho. And we see that our original equation 2 is now changed to equation 7. And now to solve equation 7, we have to adopt the procedure what we have done for linear harmonic oscillator. So on the same track, just like in case of linear harmonic oscillator, we put r rho equal to e to the power minus rho by 2 phi rho, where phi rho have to be determined. If you remember, in our case of linear harmonic oscillator, this was the solution that we used there. In that case, we used the variable xi there, and this is, and the total wave function was u xi equal to e to the power minus xi square by 2 into phi as a function of xi. Now here, since we are using the variable rho here, our wave function is defined on the same way like in equation 8. Now equation 7 becomes this one that's given by equation 9 after putting 8 in 7 and doing some simplifications. So equation 7 is now becoming equation 9, and to solve equation 9, as in case of linear harmonic oscillator, we try a series solution like this one, as rho to the power q plus s, where s going from 0 1 2 dot dot dot, or we can put like rho to the power q and y as a function of rho. So the equation 10 is simply a series solution of equation 9. Substituting 10 in 9 and equating the coefficients of rho to the power q plus s minus 2, we get a relation like q into q plus 1 minus l into l plus 1. This is some kind of differentiation we have to do. We simply for first differentiation for d phi by d rho, we get q rho to the power q minus 1 while differentiating rho to the power q, or if you differentiate this quantity as rho to the power q plus s, we get as q plus 1 minus 1 rho to the power q plus s minus 1. And while differentiating this, we have to differentiate two quantities, but for time being we differentiate only this part, neglecting this part here in equation 10. So the first differentiation gives as q plus s into rho to the power q plus s minus 1. Second differentiation gives us as q plus s into q plus s minus 1 into rho to the power q plus s minus 2. This is normal differentiation that we do, and equating all these coefficients we get relations like 11. So this means that q is either equal to L or q is equal to minus L minus 1, but this solution particular q equal to minus L minus 1 is rejected because it leads to divergence for phi as rho tends to 0. So if we put this here in phi, if we take q equal to minus L, then we will see that q equal to minus L, then if you put rho equal to 0 or in the range rho tends to 0, in that case this part will be a diverging one leading to infinity, and that's why I discard the solution q equal to minus L minus 1. And in the same way, just like a linear harmonic oscillator, we ultimately left with a recurrence relation like this: s plus 1 divided by s is equal to s plus L plus 1 minus lambda s plus 1 into s plus twice L plus 2 as given by 12. And we see from 12 s tends to infinity, then s plus 1 by s, that's the ratio of the coefficients, is equal to 1 by s. And as done in case of linear harmonic oscillator, we can show that this is nothing. If you expand these quantities and take the coefficients of them, e rho to the power s plus 1, e rho to the power s, then we'll see that they are simply the ratio of the coefficients of this quantity. And this simply means that this phi rho as a function of rho is behaving like e to the power rho. So our phi rho is nothing, phi as a function of rho is nothing, e to the power rho. So this means that our solution, putting back here in equation 8, since phi is equal to e to the power rho square, so putting this here, we get that our r is equal to now e to the power rho by 2, and if rho is infinity, then definitely this will be diverging, and just like in case of linear harmonic oscillator, we'll terminate the series in equation 10, and just by putting that a and s plus 1 equal to 0, that means we'll neglect all the terms beyond a certain time, and that particular term is having the coefficient a and s. So a and s plus 1 is 0, and like that. So we put lambda equal to this particular thing, s plus L plus 1 equal to n is equal to n s plus L plus 1, where n s is nothing but is equal to s. So just on the same track like linear harmonic oscillator, we are just terminating our series of equation 10, and by converting it into a polynomial with a condition lambda equal to this given by equation 13, and also we see that n is equal to 1 to 3 and will be later known as principal quantum number. Using 6 and 13, we get that en equal to this, because this equation 13 is nothing, it's giving us lambda, and if you remember equation 6, it's simply the energy of the system. So lambda is giving us energy, and lambda is equal to this from part 13 leads us to this energy is as given by equation 14, minus mu z square e to the power 4 divided by twice s cross square by n square. We put a subscript n here because this quantity energy depends on n, and we'll see that this is in agreement with Bohr model and also as well as experimental observations. And this means that our terminating the series, infinite series, into a polynomial with the value of lambda given by 13 is in conformation with our earlier results like Bohr's model or experimental results. Now, using this thing, in the equation 9 would now become this one that's given by equation 15. If you remember equation 9 here, this equation 9 with the replacement by 10 would lead to this equation, and ultimately we're left with equation 15. Now equation 15 can also be solved through some simplifications. We put q equal to L already, we have arrived at q equal to L and then lambda equal to n, and that equation 15 now becomes somewhat simpler from as given by equation 16. So q equal to L is already being taken by us here, and also n is equal to this quantity, lambda equal to n as given by 13. So already these things are there, and putting these things here in 15 we get this. And now putting twice L plus 1 equal to P and n plus L equal to m dash, we ultimately have this equation, this rho d to the power y d rho square, and this one. So this equation 17 is actually a well-known equation in differential equation concept, and they are having the solutions known as associated Legurree polynomial or simply Legurree polynomials. So the solution of this equation 17 is now given by Legurree polynomials or associated Legurree polynomials multiplied by constant factor, and is given by equation 18. And with the normalization conditions, we put the normalization constant n equal to this one given by equation 21, and also we represent the Legurree polynomials as given by equation 19 for different values of n, l, etc. So this is the Legurree polynomials. We can have more concepts from the mathematical physics, and with this expression 18, we can now say that we have almost solved the time independent Schrödinger equation for hydrogen atom problem regarding the radial part. So the radial wave function for hydrogen atom problem being equal to r and l, function of r equal to e rho to the power minus rho by 2, rho to the power l, y function of rho, and ultimately this part y rho function of rho is giving us this. It's simply the associated Legurree polynomials or the Legurree polynomials multiplied by a constant factor. This is normalization constant already discussed, and this is also known as Bohr radius given by 22. So with all this, with some mathematical complexity here, and on the same trick, just like in case of linear Hartree oscillator, we can arrive at the radial solution for hydrogen atom problem as far as time independent Schrödinger equation is concerned. So basic thing that we must remember here is that we are choosing this kind of parameters. Yes, equation 5, equation 6, and then equation 7 is the equation that we have to solve. To solve equation 7, we just like in linear harmonic oscillator, we put solutions like this, and we need to find out this phi, and this phi is given by equation 10. While solving for phi, we find that we have to take certain values of q is equal to l, because otherwise q equal to minus l minus 1 will lead us to diverging results. And from the recurrence relations, we will see that this particular phi is nothing but it takes an form of e to the power rho. So ultimately this r rho is equal to e to the power rho minus rho by 2 into phi rho, and that's why this will become e to the power rho by 2. But this also diverging, and since it's diverging, we terminate the series just like in linear harmonic oscillator, and we put lambda equal to this for that. And with this value of expression for lambda is given by 13, putting back in 6, we get the energy levels for this hydrogen atom problem, and this is in conformation with experimental results. Now equation 9 with the use of 10 leads to equation 15, and with some simplifications like q equal to l and lambda equal to n, already we have obtained these things, and we get an equation 16 with the further modifications lead us to this equation 17, and this 17 is nothing, is a well-known equation, and there have the solutions, the famous associated Legurree polynomials or the associated Legurree polynomials multiplied by constant factor. So with all this, the total radial wave function for hydrogen atom problem is given by equation 20. So that's what we left with some assessment here. Write the radial Schrödinger equation for hydrogen atom, that is shown in the second slide here, and then what is Frobenius method, equation 10, and then how in this problem this method is used. We can see how we have been able to find out the expression for phi here. What is associated Legurree polynomials? We have to remember this expression for Legurree polynomials, and then the normalization constant for it as given in the assessment number 4, and the final form just like this as given by equation 20. So with all this, I'm ending up this video. I hope that in the last in this series of 3 videos you'll understand about spherical symmetric potential, its application to hydrogen atom problem, how hydrogen atom problem can be solved for radial function or the radial part, and in this particular video we have solved out how this radial wave function can be obtained. So with all this, I'm ending up this video. Thank you very much for watching. Keep commenting.